what we
Okay,
can see
so that's
in our
pretty cool
telescopes and
measurement.
sometimes even our
9
naked
meters in
eyes when
centimeters.
such an
Heat's
explosion
hard to get
occurs
rid
in
of
our
in
own galaxy.
space.
For a brief time, a supernova can be as bright as the entire galaxy.
And on feet,
The most recent supernova
it's
to be
tough to
seen in our own
quantify.
Milky Way galaxy
Well, I
occurred
just need to
in the
know the
year
triangulation is
1604.
possible
It
on
showed up as a sudden,
scales,
distant, bright star
certain
and was
systems of
visible
that.
even during the day. It was
But
noted by
thinking about
Chinese
that,
scholars and was
you
studied
were
by
looking at the
Johannes
black body
Kepler.
problem as
Its
far as
remnant,
the
identified in
nuclear soup
1941,
recipe.
can still be seen
We
with our
dial it back
telescopes.
a little bit.
Now, you should know that there are actually several different kinds of supernova explosions out there,
Like
and they have slightly different. This
So
neutron
packed
star
out
is
neutrino
even more
cores
dense than a white dwarf.
on
Instead of Earth-sized, it would
your
only be
football
about
field.
10 to 20
We'll
kilometers
talk
wide,
about that
and
area
its
operation
density would
nuclear
be
soup
about
recipe.
10 to the 14, or 100 trillion times that of Earth. So a teaspoon of this
chicken
material would weigh as
patty
much
factory,
as
man.
Mount Everest. Now, the Pauli exclusion principle, which I talked about earlier, which causes electron degeneracy in white dwarfs, also applies
That's
to
away from.
neutrons
She's
in
pretty
neutron
deep
stars.
into it. From our
This is
star,
because this
its
exclusion
core,
principle
what it's
applies
doing,
to all
what it's
fermions,
gonna do.
or quantum objects with one-half spin. Electrons are fermions,
This is fun.
and neutrons are made of
Let's
quarks.
get to this.
What does this mean? Usually, this is that
Means
no
fuzzy.
more than 2 electrons.
No more than 2 electrons. See, he's gonna go exclusionary. We're Dyson talking about the spheres of higher order. What are we talking about? A up here or A down here? Gravity going up to the cloud, or is gravity coming down? As far as up and down, what's upside down? I'm looking at elements on Earth. That's what they're gonna be. It's water. There's a standard model to figuring out. Okay, so there's one of those things. There's certain ways to separate it. You can do certain things that make sense to why it is what it is or does what it does, because they're exclusionary. They're not in the bandwidth, or there's a super high probability within that bandwidth you're gonna get whatever is in that increment for what it is. You dig it up, put it in front of me, we're gonna put it on scales. Let's have forbidden S&P order about hydrogen to helium, about the carbon here, which looks like 8, right? Or 4, 6, 7, 4, 5, 6. So 6 orders here. And when you get to the S or P orders, the F orders, the few other ones that come with it, you're going to get some heavy elements. It's why at that grammafics level in a square, where you could say that is photon, gluon, W boson, Z boson, photon. We identified some exclusionary, some we both do. We can say that that's in the order. There's 2 of us in the room out of 3 of us that say, with energy, I'll get it there. I'll go up or down, yes or no, about whatever way that's going to be. Is a Z boson or W boson, filled shell, inert gas. I like ideal, because when you do what I got some of my other stuff for, it's actually very simple to go 3 miles per minute, miles per hour, certain systems where that order starts to drop off based in hydrogen. But hydrogen has to play that order to the spectrum, or you would have to line up the arbitrage of making that math pretty to do the air turbulence in the proper way, where yes, hydrogen is great for the most part, though we get a high volume of this stuff and sometimes you gotta make it, and some game
Can be in the same orbital in an atom. What does this mean? Usually atoms have plenty of space to move around in. And in a collapsing star, gravity pushes the atoms together and limits the atoms to their maximally contracted state. So what happens is that the electrons in the outermost shell of the atoms, next to electrons in the outermost shell of the neighboring atoms, create a physical barrier, keeping the atoms from compressing any further.
He had the big 3
you might
right
think
there.
that this
Our star,
physical barrier
white
is due
dwarf,
to the electrostatic repulsion of electrons in the outer shell of neighboring
star,
atoms, because
black hole.
like charges repel.
Big order.
But theoretical
M1,
physicist Freeman Dyson showed in
service rating of an
1967
M1, service
that this
rating of an
physical
M2
barrier
machine gun,
to compression of
service
atoms
rating of an
exists
M2
due
tank
to the Pauli
with an
exclusion principle,
M2
and
on
not
it,
due to repulsion
and
of neighboring
10
electrons or neighboring nuclei.
M1s
There are
attached
simply
to
no
grenade
other
launchers
free
and
quantum
anything else
states
that
for
are holding
electrons to
the field
occupy,
manual.
so there's no physical possibility of compressing more. This is the electron degeneracy pressure.
Oh, there it was.
And this pressure will pick up from where the radiation pressure fell off and take up the fight with gravity to try to prevent further collapse of the star. Once a star is in this degenerate state, gravity cannot compress it anymore because
talk
quantum
about here,
mechanics
don't supernova.
dictates that there's no more available space to be taken up.
Wow.
So the core of the
thing
star survives
about
not
that
by the
one
outward
space
pressure
movie.
of fusion, but by the quantum mechanical principles that prevent its complete collapse. This core of a star, where the electron degeneracy pressure keeps it from collapsing further, is called a white dwarf.
Blink,
This
blink.
is what will happen to our sun after billions of years, after it runs out of fuel in its red giant state. After much of its mass floats away, its inner core will be such a white dwarf. It will be the remains of our sun. It would be only about the size of Earth, but it will be about 200,000 times more massive. To give you an idea of how
Whoa.
heavy this is, Jupiter is only about 320 times more massive than the Earth.
Yeah, this thing gets
The
struck
sun
in
is
now.
about 300,000 times more massive than Earth, but it's also 110 times wider. But there's a limit to the amount of mass that such a white dwarf can have. Indian-American physicist Subramanian Chandrasekhar discovered this limit to be about 1.4 times the mass of the sun.
See, now
This is
isn't
known
that some
as
fun,
the Chandrasekhar limit.
interesting
So what
things
this
about the
means is that if
frequency
the
about
mass of
these
the
wave
collapsed star
functions?
exceeds about
They
1.4
are
times the
different.
mass
They
of
have
our sun,
changed
even this
from
electron
certain states, and
degeneracy
they will
pressure
emit
is not
certain
enough
sequences.
to
This
keep the
is
star from
a lot more
collapsing
hydrogen,
further.
a lot more
The extra
helium,
mass
iron,
can come
nickel,
from further
and
deposits of
stuff,
matter from the outer
sunshine,
shells of
some
the star.
stuff.
Once the Chandrasekhar limit is exceeded, it will keep collapsing. And what happens in this
At that
scenario
point.
is that the temperatures within the core soar to above 5 billion degrees Celsius.
And that might
At these
change the
temperatures,
phase
gamma
on
rays are
triangulation.
These are
Before
so
it'll go
energetic that they break up the iron
black
nuclei
hole,
into helium
that
nuclei,
neutron star,
also called alpha
magnetar,
particles.
quasar,
And this
or
raises
what
the
is it,
temperature even
magnetar.
higher to roughly 100
Um,
billion degrees Celsius. And
there's
at
a
these
couple of different
conditions,
ones.
electrons combine with
Pulsar,
protons in a process called electron capture to form
Sure,
neutrons.
and
This
they
process
act
also
that way
releases a flood of
because
neutrinos.
they, with that
So essentially,
spin,
once
that
the
initial state,
Chandrasekhar limit is exceeded,
made it do that some
electrons are
kind of
captured by the
differential of a
nucleus, creating
composition
a
that
smaller ball of
really
pretty much
does the
nothing but
two,
neutrons.
three things
no
that it
more
actually
atoms
could
remain.
do
The star
from
becomes like a
the
giant
football field
atomic
there, I
nucleus.
guess. Yeah.
This neutron star is even more dense than
There
a
you
white
get the
dwarf.
cube. Yeah,
Instead of
that-
Earth-sized, it would only be about 10 to 20
That wave
kilometers
function.
wide, and its density
Do the
would be
hokey
about
pokey.
10 to the 14, or 100 trillion times that of Earth. So a teaspoon of this material would weigh as much as Mount Everest. Now, the Pauli exclusion
Okay,
principle,
so where
which
were
I talked about, be visible on our telescopes, we would not see anything. That's
was
why
I?
it's called. Electron degeneracy can be overcome by gravity. Why can't neutron degeneracy also be overcome by gravity? Well, it can.
Well, space
Just like
does
the
what it wants.
Chandrasekhar limit, which when
Space
exceeded
in
results in a
that
neutron
pocket,
star,
local still
there's something
does what
called
space does
the
expansionary, but it's
Tolman-Oppenheimer-Volkoff limit,
a
or
lot
TOV
depend
limit.
on
If this TOV limit is exceeded, it results in a
that
black
doing
hole.
that. The result
Theoretical
was
work
this.
in 1996
If our
placed the limit
increments
as about
is that, and you
1.5
can't, these
to 3
guys
solar
looking at it
masses.
like, okay, so that's
So
the
if the
fuzzy bunny.
remnant neutron
I'm
star
like, yeah,
is
that's fuzzy bunny. Can I
1.5
prove
to
that?
3
Well,
times the
if I
mass of
scale
our
that
sun,
down to 1 inch,
gravity can overcome even the
and I got to do
neutron
orbitals,
degeneracy
and I
pressure
put with those little
and
orbs
collapse
Jupiter.
it
And
further
Jupiter's supposed to
to
be how
something
many
even
numbers?
smaller than a
Hydrogens with how
neutron
many?
star. Theoretically, infinitesimally small, it can form a black hole. This is a complete domination of gravity over every other force and is an object beyond the limits of our equations. When a black hole forms, nothing can escape from it,
There's all
not
the
even
rest
light.
skeletons
So
in
unless
there.
there is infalling matter into the
Every
black hole,
step
which
on
gets
the ground,
compressed
you know,
and heated
you
to produce high-energy
should be
radiation
able to
like
put,
X-rays and
if
gamma rays,
you had a
which
300
would be
by
visible on our
150
telescopes,
foot
we would
stadium
not see anything.
football field,
That's
I
why
think,
it's
what
called
is
a
it, you can
black
get
hole.
50,000 people
So
in there,
a white
something
dwarf
like
and a
that,
neutron
700,
star
or
due to
700,
the same root effect, the Pauli exclusion
700
principle. Two
and
fermions
50,
cannot be in the same
something
state,
like, alright, so what
including
is it? I
position,
wanted
so they
300
form a barrier to further
by
compression.
100,
The
I want
difference is the
20,000
type of fermion.
people
in
in a
the case
football
of white
field.
dwarfs,
That is
it's the electron.
300
In the case
and
of
just
neutron stars, it's a
360
neutron.
feet, end
In
zone
white
to end
dwarfs,
zone,
as atoms get tightly
and
packed together,
160.
the electron's
you will
wave
get
functions
at a log
overlap
18
more and
squared,
more with the neutron's wave function. And so the probability of
26
electron
or
capture
20,000
increases.
people in there.
Eventually, a white
Just
dwarf
standing there.
can thus
They can
become a
hang.
neutron star when gravity is high enough. The neutrons in a
What we
neutron
can do
stars,
with
however,
them?
don't have anything to get captured by. So they can get very densely packed. But gravity seemingly has
Seems
no
like
end
wrong
and can
increment
keep
for
going
our,
if the star
kind of
exceeds
wave
the
function
TOV
tracking
limit
that bunny,
to
just running them,
ultimately
smoke them
form
all day,
a black
all
hole
day, just run.
beyond the
They
limits
drop,
of
take
quantum
break,
mechanical
then
laws
run
we
more,
know about.
and run more, and run
These are
more.
some of the most
Some space
interesting
marine's just
and
gonna
fascinating objects in the universe. Now, if you want to learn more about the science of gravity and black holes, there is a superb college-level course on Wondrium, today's
power
sponsor,
up, or
called
will you?
Black Holes, Tides, and Curved Spacetime, Understanding Gravity.